Yeah, today we'll discuss the remaining part of solar air heaters. Yesterday we have discussed about the plastic air heaters. Okay, in this plastic air heaters we discussed about some applications like solar greenhouse effect, which is required for the agricultural purposes. How their air heating is done with using plastic air heaters, and also we discussed about some of the tunnel type of air heaters where the length and surface area is increased by using some metal structure to support this flexible plastic covers. Okay, simple plastic covers which are black surfaced. These type of applications we have discussed in the last class. Next application is the unglazed transparent collector. It is also called as UTC. Okay. And network is clear, no?
Yes, sir.
Okay. So this is shortly called as UTC also. So earlier we discussed this type of applications in trompe wall or the building room heaters or the space heaters, where this wall can be heated by the solar rays and we can heat the air, and some window can be prepared or the outlet or the inlet can be prepared at the top of the wall where hot air will flow from the below point or the bottom point to the upper side. Same concept of our trombe wall or the space heating applications by the using wall side heatings. Same type application here also is used. So one main important change here is in the unglazed transparent collectors is we are not going for the glazing or we are not using the glasses in front of the big buildings. Okay, so in spite of using that glasses to increase the space heating effectiveness, here what is done is this perforated absorber plate is used. Okay, so this perforated absorber plate, if you see, this may be constructed with the building itself. Like in the building, you can see here with windows. After that, windows, any space is left out, so you can go for the metal platings like this to prepare a perforated layer. Okay, it is just having some area there. After some keeping some gap, you can construct these type of perforated plates of metal or it may be a concrete structure. And later the painting may be dark color paintings can be done on this perforated layers, so that this type of construction what it will help is, so whenever the solar radiations fall, say for example on the east side or on the south side, sorry, in the west side, so both side whenever the sunrise and sunset is going to take place, so maximum time what happens in the sunrise time, the cold air inside the room which is available in the night, that should be heated up or the heating of the room is required. That is one thing. And in winter season, after heating in the morning, in the evening also, when the air starts moving in the building with cold air, okay, that should be also heated. So that can be done on the preparing the perforated absorber plates on the opposite side of the building where the sunset is going to happen. So due to that sunset solar radiations, one can heat this air on the west side, okay, and he can heat the room where the air may be moving from the east or west or in any other directions. So the heat can be collected from the east or west side because of the solar radiations, and one can heat the chamber or heat the room inside this building. Similarly, apart from these concrete or metal plates, one can also go by these plates. Here you can see the below side. I have taken one example where the channel type of metal plate is there. So this metal plate, to improve or to increase the maximum surface area, they have made a channel like structure, and in these channels if you see, the surface area is perforated, it is having small holes, okay, throughout this channel. It may be in vertical line or it may be kept in horizontal direction, such that whatever the air is heated at the bottom side, say for example vertically it is connected, say for example this is the bottom side, okay, and what we are seeing the perforated points, it is at the top side of the building. So what will happen, the cold air, okay, the cold air can enter easily inside these plates, or whatever the air at atmospheric conditions is available inside these chambers or inside these plates, okay, can be heated by heating the surface plate itself. So that principle is shown in this layout. So the line diagram, if you see, the ambient air can pass through these perforations, okay, at ambient condition only. Then once the metal plate or the concrete structure, once it heats up, okay, which is in front of the building, once it heats up, the air which is in contact with the chamber is also going to heat up. So that chamber is called as plenum of air here. So similar word I think you have used in energy engineering or other subjects. The plenum of air, whatever is available at the bottom side. Okay. So once it starts heating from the bottom to top surface, the temperature of the air is going to increase slowly. It is going to absorb the heat from this unglazed surface, like metal surface with perforations, or it may be a concrete structure with some perforations like this. Okay. So once it heats up, that hot air can be taken to the room. So either it may be a natural convection or you can use a blower or a fan inside the room. And due to that, what you can do is, for a given amount of or the mass flow rate of air to be maintained in the buildings or in the industries or in the application to the different drying purposes, there you can go for using some blowers or the fan. Then you can supply this hot air to the given rooms. So this principle is similar to the Trombe wall or your glazed surfaces of buildings or any other surfaces. Okay, same principle, but here change is what? In the in place of glazing, in place of glasses which are used here earlier, or with the in place of concrete structures, what you are doing is we are using a perforated surfaces. That is the only difference. So if you are going for the perforated surfaces like this, then it is called as unglazed. Without glasses, it is called as unglazed. Transpired, because air can transmit easily and it can come out also anytime. So it can maintain the atmospheric conditions. So once the heating of the chamber is going to start, then only the heating of the air is going to start. So this type of application is called as unglazed transpired collector, or in short, it is called as UTC air heaters. Okay, so this is the last part of different types of air collectors. So totally we have discussed these many types of solar air heaters. Those are without fins, with fins, absorber plate, or V-shaped or the corrugated surface of the absorber plate. So these we discussed. Then we discussed two pass air heaters in different type of or various passages of the air inside the absorber plate itself. Then we discussed recycling of the air channels. So after heating the first cycle of air, it is mixed with the second cycle of air and it is recycled continuously. And whatever the part of the air is required for application, only that part of air is taken to the outside. That we discussed. Then we discussed about the matrix and porous type of metal matrix, where the reflection and refraction can be increased, so that absorption of the metal can be reduced by this porous medium or the matrix medium. That we discussed. Then we discussed about the combination of this honeycomb and matrix structure also, with fins and honeycomb structure or the matrix structure. Then we discussed about the staggered type of plates or the absorber plates, how it is connected here, so that in multiple layers the air may be heated up at a given temperatures. So as you increase the length of this absorber plate, the amount of temperature what is added to the air is also more. So like that, for a given different chambers, the different temperatures can also be maintained by maintaining number of glass covers and number of absorber plates. That is a staggered type of air collectors. And also we discussed in the last class modified solar collector or a concentrating flat plate collector. So by using just more number of reflectors apart from a general or a conventional air heater, just by using the reflectors as many as possible, we can improve the more reflections on the same absorber plate. So this may be also come into picture in concentrating type of solar collectors. That principle is used here. Then we discussed about the plastic air heaters, and today we discussed about the unglazed transpired collectors. So this is all about the types of air collectors, conventional, non-conventional type of air collectors we have discussed. Now next we'll take the performance analysis of the solar air heater. So this is the topic which is there in the syllabus we need to discuss. So in this we'll not discuss the detailed derivation of the steps. We'll discuss the important equations which are there in this topic. So how to write the balanced heat equations or useful heat gain equations, then our flow rate or the flow factor, what we call in the liquid flat plate collector. Same parameters also used in this air collectors also, like your heat removal factor, efficiency, collector efficiency factor. Okay, so all these things we are going to again see in this air collector. So we'll discuss some of the important equations and how those equations are achieved. And probably I think in this part we don't have numerical, but still I have taken one numerical as an example that you can take it as homework later. Okay. The connection is continuous, no? Audio and video.
Yes, sir.
Okay. Yeah, in this performance analysis of air heater, you can observe an air heater with a simple plate without any liquid tubes. What you can say, the liquid tubes in the uh, flat plate collector, that we are not using here in the air collectors. So it is a flat plate, simple flat plate without any tubes. So that flat plate is here. Okay, the black color thick line what you can see is the absorber plate. So this is shown here with the arrow mark, an absorber plate. Above that one glass cover is shown. This is just for the reference purpose. You can have 2 glass covers or 3 glass covers, it is left to you. So here it is, for notation they have shown one glass cover is shown at the top, one absorber plate below the glass cover at some distance. Below this we have a bottom plate. So bottom plate and the absorber plate both are made up of metal plates. Both are going to heat, okay, by absorbing the solar radiations. So absorber plate is directly coming into contact with the solar radiations after transmitting the solar radiation into glass cover, and that will be absorbed by the absorber plate here. And after heating the absorber plate, we are going to heat this bottom plate, or the bottom plate is going to heat up by having the convection heat transfer from the air to the bottom plate, or also with the radiation. So radiation heat transfer between the absorber plate to the bottom plate. So like this heat is going to transfer from glass cover, through the glass cover it is going to transfer to the absorber plate. Then indirectly it is going to flow the heat as a radiation process from absorber plate to the bottom plate. And below the bottom plane you can observe here, this is the insulation. What are the gray color uh, color is made here with some thickness. This is the insulation part. So all the materials and other things are similar to the flat plate collector itself, or the liquid flat plate collector only. Only difference is the tubings is not done here, or the channels are not done with the absorber plate, because the air is passing. So air can be passed in the channels also, in the tubes also, or it may be a flat plate also. So generally it will be a flat plate without any tubings. Now taking the dimensions of this as a reference, I can assume the length, total length of the collector in the direction of airflow as L1. Width of the collector, for our reference I can consider W, the width of the collector. So in the bottom side it is shown front side view. Okay, in the side view, in the top 3-dimension view you can see, or the isometric view you can see the width, the length and the height of the collector, all you can see. And the air passages, if you see, the air may be moving, okay, air may be moving in between the absorber plate and the bottom plate, as we are assuming the more heat what the air can absorb is between these two metal plates, not with the glass cover and the absorber plate. So air movement is considered here between the absorber plate and the bottom plate here. That mass flow rate is considered as m dot, and the inlet fluid temperature is considered as TFI. The bottom plate and the air, the heat transfer coefficient between air and bottom plate, you can consider it as H2. they have considered, or you can consider HFB because it's at the bottom side. Then the plate side or the absorber side, if you consider the heat transfer coefficient with respect to air, that heat transfer coefficient can be denoted as H1 or HFP. Okay, HF is the heat transfer coefficient between fluid and absorber plate, that is denoted by HFP or H1. And the outlet temperature of the fluid is shown here, TFO. On both sides, the outlet flow of the fluid, if you see, it is denoted by TFO. And also we have seen in the liquid flat plate collector also, the top losses are denoted by UT, bottom losses are denoted by UB, and especially in this air collector, we are going to neglect the side losses, because here the water is, or the liquid is not flowing only inside the collector, and it is not collected after this piping connections. What is happening here is the two complete sides are open to the atmosphere such that the air can easily flow through the passages. Okay, and we left with only these two sides towards L1, towards the length, we have two sides which are closed. So maximum area is open to the airflow itself without having any pipes or small channels. We are assuming there is no heat loss between the sides in the air collectors. But in the flat plate collector, we have taken some equations where the side loss is also considered. So here we are going to consider only bottom losses and the top losses. And later we are going to assume this bottom loss is very less compared to the top loss because of the good insulation properties. Now to analyze or to write some heat balance equations or the useful heat gain or the efficiency factors, we are considering some small section here. This is the small section of thickness dx because it is in the direction of x, okay, or in the direction of L. We have considered dx or dl, the width of this small slice or the absorber plate. If you see that, we have considered length of dx. Then the fluid what is entering and leaving this small section, if you see, it is going to be added by some small change in the temperature. Okay, because all of you can agree with TFO. TFO will be higher than the TFI, or the outlet temperature of the fluid will be always higher than the inlet temperature. Similarly, for a small change in length, okay, small change in length or small flow of air here, TF is also increased just by small amount of temperature. So that is denoted by TF plus TTF, or delta TF also you can consider with respect to dx. Change in the dx, there is an increase in the temperature of the fluid. And similarly, the mean temperature of the absorber plate is considered as TPM here, the mean temperature, or naturally you can consider the plate temperature as TP. And here bottom plate temperature, if you consider mean, I can consider as TBM, or generally if you consider at a point, local point, I can consider it as TB, the bottom plate temperature. So similarly, all points are shown in the top sketch also. Okay, so this is about the considering a solar air heater, a general solar air heater for the performance analysis. Now coming to the heat balance equations on different parts of this collector, we are going to focus here on the heat balance on the absorber plate, heat balance on the bottom plate, and the heat balance for the air, because we are focusing more on the heat exchange between absorber plate, air, and the bottom plate. So we are writing the heat balance equations for the three surfaces or three materials. So first material is the absorber plate. So on the absorber plate, whatever the heat is collected by the solar radiation, we are denoting it by S. Okay, this S is the solar radiation absorbed by the absorber plate. Or you can recall the flat plate collector equations, that is HR into tau into alpha. Okay, that polarization or the transmissivity, absorptivity, Snell's law, all different concepts remain same for the solar air collector also. But here we are more focusing what is the change, or the how the equations are going to change with respect to flat plate collector and the air heaters, because here we are not considering the plate as a fin. That you have to keep in mind. We are not considering the absorber plate as a fin here, because it is not acting a extended surface for a tube. It is a complete surface, and here we don't have the pitch of the tubes or the width between the tubes. We don't have, and we don't have the diameter of the tubes also, as we considered in the liquid flat bed plates. So neglecting those terms, what will be the effective heat removal factor or the flow factor or the efficiency factor, that we need to focus. I hope you are getting the point. So now this S is the absorbed energy or the energy received by the absorber from the solar radiation. So this you can recall as I into tau into alpha. Okay, that I is nothing but the solar radiation on the absorber plate for a given hour, or you can consider it as H also. Maybe for a day, how much is the solar radiation falling on the given surface? So H into tau alpha. That tau alpha is nothing but the after glass cover, how much it is going to transfer with the absorption of the energy. So that I into tau alpha or H into tau alpha or HR into tau alpha, I am just denoting by S. That is the solar insolation or the solar radiation received by the absorber plate on this area. So area is W into dx, means we have considered W is the width, and this strip, small strip you have considered. Later we are going to integrate it from 0 to total x. We are going to integrate. Until that we have considered only for the small strip here. So for that small strip, what is the solar flux falling? The solar flux falling is S into area. What is the area? Width is W, not changing, but x is changing with dx. So we have considered S into W into dx. So whenever the W into x term comes, you assume that is the area of the plate. So that energy is going to be lost now. So that's why I'm writing equal to, or you can write the received energy as positive, lost energy as negative, equal to 0 also you can write, so that you can tell heat balance is done. Or else I can write it as energy received on left side, energy lost on the right side. So energy lost is in different forms. One is with the loss coefficient in the top side. Okay, in the top side it may lose by convection or radiation. So I can take it as top loss coefficient ut with respect to given area, W into dx, and delta T. What is the delta T between top and absorber plate? It is Tpm minus ambient air temperature Ta. And just see here, the absorber plate is here. The temperature maintained with the absorber plate is what? Tpm. This loss is going to happen from the absorber plate to the outside atmosphere by ut. So this ut into area of the surface. Area of the surface you have considered dx into W. Temperature difference is Tpm with respect to absorber plate minus the outside temperature. If you consider, I can consider T ambient. So with respect to that, I have written T ambient plus heat from the absorber plate is also lost through the air which is passing between the bottom plate and the absorber plate. So I have considered H1 here. So H1 is nothing but this heat transfer coefficient. H1 is HFP, heat transfer coefficient between absorber plate and the air is HFP. So I'll consider H1 as HFP into area into Tpm minus Tf, because it is taking place between the absorber plate and the fluid. I can write the difference of temperatures Tpm minus Tf plus the same heat from the absorber plate is also lost, okay, is also lost to the bottom plate by the radiation process. So here, as the heat is transferring from the top surface to bottom plate, in this sketch you can just see here, from the absorber plate to the bottom plate it is moving. Okay, so this bottom plate is not exposed directly to the sunlight, so it has to receive the heat either from the fluid, through the fluid, or without air also you can assume that the heat is transferring from the absorber plate to the bottom plate by radiation process. So to write that, we can go or recall the radiation equation or the radiation process equation, that is sigma into A. Sigma is the Stefan Boltzmann constant for radiation. divided by 1 by epsilon p. So epsilon is the emissivity of the plate, epsilon b is the emissivity of the base. So it depends on the emissivity of the two plates. So that's why I have taken 1 by epsilon p, 1 by epsilon b minus 1 into, in the radiation process we are taking the temperatures raised to 4. So we have taken here tpm raised to 4 minus tbm raised to 4. So like this, whatever the energy absorbed by the plate, absorber plate, is lost to the top cover or to the top area in atmosphere. That is the top loss we are calling it as. Then the bottom loss is with respect to bottom plate, and bottom loss is also possible because fluid is absorbing the heat from absorber plate also. So there are totally three terms on the right hand side, three losses. The received energy is on the left side for the absorber plate. Now, as I told you, for the bottom plate, if you go for the heat balances, so I can recall for the bottom plate, whatever the energy received is by the radiation process from the absorber plate. So keeping that in mind, I can write the same equation as it is here, because the radiation process is going to take place between two plates. Sigma W dx, that is area, divided by 1 by epsilon p plus 1 by epsilon b minus 1 into bracket tpm raised to 4 minus tbm raised to 4. So this is the energy received by the bottom plate now. And as I told you, left side I can take the energy gained. Right side I will write the energy lost. Now energy lost from the bottom plate are in two forms. Okay. Where it is losing the energy? The bottom plate is losing the energy. One is at the bottom or to the insulation part. It is losing the heat, very negligible heat. And some heat is lost to the air. I hope you are getting. And is not losing heat to the plate. Why? Because the absorber plate is will be always having higher temperature to the bottom plate when the solar radiation taking place. So keeping that in mind, we have considered the heat is lost to the insulator or insulation. So that can be written as loss coefficient at the bottom with the area W dx into TBM minus TA. Because the bottom side, if you see the insulation part, it is kept at the atmospheric temperature. It is exchanging the heat with that. Similarly, the fluid which is flowing in between the two plates, there also it is losing the heat by convection process, because the fluid air is flowing. That I can write it as H2. Why H2? Because it is the heat transfer coefficient between the fluid and the bottom plate, HFB. So that HFB, in place of that I have written H2. Second heat transfer coefficient, where the air is exchanging the heat from bottom plate. So that H2 into area W dx into TBM minus TF. So in all equations you can just cancel W dx because it is common for all the equations. You can cancel it later and write in the short form also. And for the air stream, if you see, or for the fluid, if you see, the energy absorbed by any fluid, if you recall the equations from the heat transfer or fluid mechanics or any other subjects, we can write it as mcp delta t. Or the in the engine, the heat absorbed by the coolant, you can recall that equation that we are finding by mcp delta t. That cp is the specific heat of the fluid, depends on air or water or any other fluids. That cp value you have to consider for air here in this subject. And in the flat plate collector we have to consider for the water, because water is heated there. So that is written as heat received by the air is m dot cp dtf at the fluid temperature. Okay, minus, now you can see why I am writing dtf, why not tbm minus tpm? Because here we are considering only for the small strip. For the small strip I am considering the exchange of heat. That's why I'm writing small dtf. What is the increase in the temperature is there? If it is not like that, I can write with tpm, or I can write outlet temperature of the fluid minus inlet temperature of the fluid. Like that also I can write. What is the rise in the temperature is there? we have taken dTF for the small strip equal to, now where the air is going to lose the heat. First thing here is air is actually not losing the heat, but only when if the air temperature is higher and the solar radiation suddenly falls because of the diffuse radiation or some other radiations, there may be some losses will be there. So in such conditions, I can go for the losses with respect to either it can lose the heat to the bottom plate, or it can lose the heat for the top plate. So once you add these two things, I can write it as H1 A into delta T with respect to plate temperature and the fluid temperature, plus H2 into area delta T. Okay, so this temperature difference is between bottom plate and to the fluid or the air. So that is considered. So here now we have written all the three heat balances equations for the three surfaces where the exact heat exchange is required for the application part. So I hope there is no doubts in these equations.
No, sir, no
Okay.
doubts.
So here you can just remember the heat exchange between the surfaces so that you can remember these all equations. If you try to remember these equations, it is very difficult. But if you try to remember the concept or the process, how the heat exchange is going to take place, one can easily remember these equations. Just a minute. Yes, coming back to the class. So now we are going to simplify all these equations by putting some combined equations or some effective terms. So here an equivalent radiative heat transfer coefficient, that is HR, is introduced a new parameter here. So this HR represents the combination of both, or you can tell the combination of radiation heat transfer. So with respect to that radiation heat transfer, in place of sigma divided by 1 by epsilon p plus 1 by epsilon b minus 1. So in this big term, and T pm raised to 4 minus T bm raised to 4. So we're going to replace this entire term, keeping T pm raised to 1 minus T bm raised to 1 as it is. We are writing as HR. Okay. So what is HR here exactly? If you simplify this T pm4 minus T bm4 at very low values of difference in plate temperatures, if you take bottom or top plate temperatures at very low temperatures, this raised to 4 minus raised to 4 can be approximated as 4 into T average raised to 3. If you consider two plates and average temperature, I can write it as T average raised to 3 into bracket T pm minus T bm. Again, if you multiply, I can write it as 4 into bracket T pm raised to 4 minus T bm raised to 4, like that. Okay. So this can be written as 4 into T average raised to 3 T pm minus T bm. T average can be again written as T bm plus T bm by 2. So in place of these all equations T pm minus T bm, we can substitute as HR equal to So only considering this TPM minus TBM as a separate term, now we can write it as this sigma into TPM raised to 3 minus TPM raised to 3 divided by 1 by epsilon P plus 1 by epsilon B minus 1. As after simplification, we can write HR as 4 sigma T average raised to 3 divided by 1 by epsilon P plus 1 by epsilon B minus 1. So this is taken just to simplify. So what we are going to simplify finally, because we need to keep all these temperatures raised to 1, not raised to 4. So for that purpose, they have considered HR as a simplified term, so that these all epsilon terms, sigma value or the temperature raised to 4 or 3, all are neglected. So if the heat transfer coefficient with respect to radiation is directly given in the problem, or you can simplify and take this HR value directly in place of sigma and epsilon values, I can write HR. So similarly, now I can simplify that W dx, what I told earlier, you can cancel W dx throughout this equation. So that is done here. Area is cancelled because area is multiplied with all the equations. So that is cancelled. Now I can write S equal to UT into TPM minus TA, same equation, plus H1 into TPM minus TF, H1 into TPM minus TF, plus, see here, plus HR, we are going to replace this big term with HR, heat transfer coefficient with respect to radiation, equivalent radiation heat transfer coefficient you can recall. So that HR is written here. Then TPM raised to 1 minus TBM raised to 1. That is written. Okay, so from this equation, we can find out what is TBM. Okay, or TPM we can find out here. TPM equal to, after simplification, you can just remember here, it can be simplified and written as S plus UL into TA, because UL into TA is minus here on the right side. If I take it on the left side, it will be positive. With respect to S, if you see, UL into minus TA will become plus UL into TA, like that. Plus HE into TF. See here, this is again one new term, HE into TF. So this is also a effective heat transfer coefficient, because here TF into H1, whatever is taken, or TF into H2, it is with respect to H1 and H2 and HR also. So keeping these all terms as an effective heat transfer coefficient, okay, so that effective heat transfer coefficient they have written as HE into TF divided by UL plus HE, like this. Then next term is with respect to this equation, second equation for bottom plate. If you see here again, it is replaced with the HR word, and W dx area is replaced or cancelled. W dx is cancelled. Now they have written HR into TPM minus TBM on the left side. On the right side, we have left with H2 into TBM minus TF plus UB into TBM minus TA. See here, H2 into TBM minus TF. See here, plus whatever UB was there. Okay. Now, as I told, the bottom losses, if you neglect, or if you consider UB is very less than UT, very less than UT value, then we can cancel this last term. So after cancelling, we have left with only these two terms, HR and H2. So from this equation, we can write TBM. Okay, or you can take reverse also. From this equation, you can write TPM. From this equation, you can write TBM, and you can substitute in another way. So here what they have done, from second equation here, from this equation, they have written TBM as HR into TPM. Just see the words here, HR into TPM plus H2 into TF divided by HR plus H2. Now this TBM word, whatever is found here, this is substituted in first equation, TBM. With respect to absorber plate equation, whatever is written, here TBM is replaced with this full big term. So once you replace this TBM here, okay, and TPM can be written as, TPM can be written as, or also substituting this HE value, because once you substitute TBM as HR plus TPM plus H2 TF divided by HR plus H2 in only this equation, in this term, with respect to TBM, because TBM is only one word. Once you substitute, okay, that HR, H2, and this equation in this what we are finding H1, HR, and in this TBM we have HR. So that HR, H2, all these terms will be combined here. So effective heat transfer coefficient, whatever the term is after simplification, you will get H1 plus HR by HR H2 divided by HR plus H2. So this equation or these terms we can replace with HE just to simplify. Okay, so that is simplification by substituting TBM from this equation, and TPM also you can substitute in this term so that you can find out HE term. So once the HE and TBM and TPM is substituted, then we can write TPM minus TA from the first equation. I can write TPM minus TA equal to S plus HE into TF minus TA divided by UL into HE. Like this we can write. Then for the again coming back to the air, this is the simplified form for the first equation, TPM minus TA equal to S into this. Then for the air, whatever is the fluid is flowing in between the plates, MCP delta T, that we know already. Then the WDX, okay, WDX, whatever is there earlier, see here in this equation, WDX, whatever is there, now that is taken in the denominator. Or from this equation you can see MCP dt, WDX is common for this air stream on the left side. Whatever the heat is lost from the area of the heat transfer surface. So this WDX common term is taken in the denominator side here. So for that air stream, I am taking MCP by W, dTF by dx. So I'm just segregating the words equal to, now what we have done here is these terms, whatever is there, H1 WDX TPM minus TF plus H2 WDX TBM minus TF. These words we are going to replace, okay, we are going to replace with the first equation. That is, I can write it as S minus UL. So just what you can do here is to remember in this first equation, S equal to whatever is there, TPM minus TA is not there here. TPM minus TF, it is there here. H1 into TPM minus TF is common term. Okay. Then H2 is not there. Okay. So keeping this TPM value, TPM as S plus ULTA plus HE ATF divided by UL plus HE, that you can substitute in this TPM. That is one form. Okay. Then TBM, you can substitute in this form. Then again in the TPM, you can substitute S plus UL. So like this, if you go on recalling just the words and these substitution words, after simplification, we will get as S minus UL into TPM minus TA. Because finally we want the useful heat gain equation that we are finding. So to recall this useful heat gain equation, we need the equation in this form. I think we'll stop the class here because time is 4:20. In the next class, we'll complete these important equations and we'll define some of the factors, and we'll take one example on numerical. Okay. Then we'll complete this fourth chapter. Okay, I'll stop the class here. Tomorrow, I think tomorrow Thursday, Friday we'll discuss this again.